Testing. Testing 1, 2. Let's open our virtual machine and let the world know that we are live. Do, 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 do. Okay, let's get Debian launched. Da, da, da. Hold your horses, VS Code. We're not there yet. Deprecated extensions, hey? Cool. There we go. And everybody's happy. And Chili. Hello there, good sir. First viewer of the day to say hi. How you doing? I'm just gonna do a quick check. I've been messing around with the sound and I want to see if the bit sounds are coming through. No. Not cool. Try that once more. Da, da, da. Hey, I think that worked. That was the soundboard. So at the bottom of the chat, if you click your channel points, you can spend them on silly sounds. Hello, Reb. Good evening. So today's stream is FADD, and that is a fuckabout driven development, I'm afraid, because we're at a bit of a sticky point. I didn't stream over the last 3 or 4 days because of there wasn't much code to do. I had to do a lot of R&D into stuff around memory management, and I can't get away from it anymore. It's staring at me in the face, saying, implement me. So we need to take this bull on by its horns. And flesh out the, not only develop the physical memory manager a little bit better, but we're going to try and set up the virtual memory page tables. Now that we understand them, my aim today is going to be creating a page table entry, initializing a variable to that virtual memory location, and see if I can read write fine. Then I'm going to try and block that memory location and see if the same read write will start causing a page fault. So it literally is like it's a complete fuck about with virtual memory day. I have no idea how entirely it's going to work. I have a feeling of what I need to do. But the information on it is so vast. It's a massive topic in the software development manual, and it's a very poorly documented, I would say, on the OS Dev Wiki. Like, there's so much old information around 32-bit memory addressing and things that you don't have to do anymore. And there isn't like a full-on Hello World 64-bit paging tutorial that I found. So yeah, I've got a point. So, you know, I've got the theory in my mind of what we're going to do. And I just need to see if it works. But before we do that, we're going to dip back into our memory module that we have and expand this guy from a simple bitmap. So it's a bit of a poor implementation, and it got me going at the beginning, but the bitmap does not track how many pages have been allocated. So I can't free memory safely. So it's an allocate only memory manager at the moment. So I need to expand it beyond it being a bitmap, and I need to kind of enrich the metadata around the bitmap so that we're tracking multiple pages being allocated, we're mapping the length, and we can then free pages. So I'm gonna be a bit newbie at this as well, because I'm not entirely sure how I'm going to implement that either. In my mind, in theory, it should be simple, but I'm going to stumble, I think, when I'm doing some C things, but hey ho, that's how we learn, right? So the reason I've had to take a side quest onto doing this memory stuff is because getting into the NVMe, which we're really close at talking to the NVMe controller. So we got to a point in the last stream where we resolved the base address of the NVMe registers, which was a huge milestone in itself. But our memory manager kind of lets us down up to this point because we don't have a way of creating page tables, so we can't do a proper cache of like, I'm not sure exactly, but I need to use the page tables for caching purposes, memory performance. So that's kind of what's pushed me right from this point here on giving up on the NVMe for now until we've developed the virtual memory manager. So this is going to be a really struggle bus stream, I'm afraid. as embarrassing as it's going to be, but you know, we will have a lot of fruits if we get through it. And if it was all easy, then it would be too. Anyone could do it, right? Figured out what archetype you are. No, but I can probably have a good idea if I look at the list. Let's have a look. What's our archetype? It might be in the introduction. It might not be. Beginner mistakes, maybe. Nope. How about getting started? Oh, is it in what order? Okay. All right. Let's have a look. The Lino Commando. First thing he wants to have is a blinking cursor after a greater than symbol so they can type commands. No matter if there's no way to start two programs at the same time, he just needs a text editor and a file system driver. Oh my god, that's it. What did we, our roadmap so far is, oh, I just need a console. I just need a terminal. And then we're going to do a blinking cursor because we want timers. And now that we have a console, we need a file system. So, first one ticks the box. Jesus. His test machine has no keyboard and no screen. Oof, definitely not us. I was tempted to go down the UI route first because it would be fun to do some UI programming, but I realized that would just be UI programming and it's not true OS dev. Works in a dark corner of a small room with listings all around. Her system has much evolved since last year, that all she can show you is still the same bunch of A and Bs displayed in no obvious order on a text console that she controls with magic key combinations. Oh, that's interesting. That would be the true back-end engineer approach of just working on cool code stuff and not actually controlling the PC. Excuse me. A new language for a more elegant operating system spends at least much time on a new language design as system design. Well, not terribly impressive code for the areas he's unskilled in. I guess this is all like for experienced OS devs. Given that this is like my very first operating system ever, my very first experience into embedded programming, it's kind of, it all falls into place as like the only thing I can do. Like doing a monolithic kernel at the beginning and everything in ring zero is kind of like the obvious choice for a newbie, right? It's the easiest. Like no seatbelt on, no worries about loading modules. Like if I was ever to tell someone if they were coming into OS dev completely new, I'd be like, yeah, just it's your first one, man. Just code everything in one project. Like, who gives a shit? Like, stick everything in the kernel. You'll realize after you've done all that why that's not a good idea. And you can start again, or at least even break apart the one that you have, which is my plan. But yeah, mine was definitely the naive. It was definitely a cowboy approach. And it was definitely this first one, the Lino Commando. It's described me perfectly. The first thing we wanted was to have a blinking cursor. What's my resolution? Good question. I think this is a 2K monitor. Yeah, it's in 2560 by 1440. But I zoom all my pages in, so like Chrome here is at 175%. If I was to read stuff at 100, that's just horrible. So I'm a bit of a zoomer now. Okay, so I think we should dive in. Which takes us straight into our memory module. Now, okay, let me think about this because I'm going to do a bit of a planning. All we have right now is this humongous array of bits telling us that our pages are on or off. Now, when somebody comes in with an allocation, they when they allocate, they get given back a memory address, but they may have asked for multiple pages being switched on, or that memory address had that many pages switched on. So when you come to free that information, so the key alloc is what we have. There's I want 100 bytes, and that will give you one page. And if you ask for, I don't know, 5,000 bytes, page size is 4096, you'll get 2 pages. Now, when I come to free that information, which at the moment I can't free that pointer, I need to turn off these 2 pages. Now, to do that, I need to understand that address. I don't know, let's pretend it's got an address. And we need to say what its size was in pages, right? That's the metadata that I want to store, that allocation. But to make my life easy, what I could do is at each bit location for the pages, I could have an array of metadata, right? So we could say have a struct. I guess literally all I need to say is the length for now, right? And that's the amount of pages that you've just taken. So if our bitmap is 1,000 pages, we'll have a 1,000 of these. So then when we get a free call, so someone comes in with a free and they give us that memory location, we can map that memory location back to a bit, which gives us an index into this array. And once we've got an index into that array, we can look at the length. the bit tells us whether that memory location is taken or not, but the length at that point in the bitmap or in the mem entry array would tell us how many pages we allocated. You should have 1 byte to identify every byte. That way it's not wasting space. Are you trolling me, Fly Mario? So yeah, we're expanding the metadata of the entire memory manager. So this is taking physical space in memory, the number of pages and the bits. And then we're going to have that struct, supporting struct, which I guess will just live. Where will that live? Will that be a heap allocation as well? Because we won't know. Yeah, we won't know on a given system how large the bitmap is. So we'll have to resolve this length at runtime. So we'll have to do another heap allocation in the memory map, a manual one. We'll need a place for this structure to live, and then we can get a pointer to that. And then, yeah, just plug that into this whole KLOC and free stuff. And what I'm doing with, I'm kind of nervous about keeping it as a memory length allocator. So a lot of OSs, what they're doing is keeping their physical memory manager as a page allocator. So you don't ask the PMM for 5,000 bytes, you ask for 2 pages. And then the virtual manager is the thing that allocates things by bytes. But that whole chain of design, I have no clue yet on how we click things together. So I can't really see a point on changing this design yet. And when we come to do the virtual, I really need to just mess about with how that works, and then hopefully something clicks and tells me why you'd want to keep the PMM as a page allocator and maybe why the VMM is only a byte allocator. I don't know. But that whole system design is a bit confusing for now. Thinking of it at the physical level, no problem, but the virtual level is very mind-bending. Yeah, so we'll get this struct realized, I guess. Thank God that I've code docked all of my old code. Well done, past Martin. You did a good job there. What should we call this? Should we just call it page entry? How many pages did my logs report when it booted up? I think I dumped that. Total memory, 2 gig, total map pages, 524,000. Yeah, I think a uint 32 will be fine for that. Number of pages allocated for this page entry. I kind of don't like how it duplicates though across every bitmap slot, specifying a length. It's kind of weird. But I guess you can't really get around it. Hmm. Now, where did I define my bitmap? Page bitmap here. So yeah, that bitmap tracks all the pages in the entire memory map from the lowest and the highest points in the memory map. Bit value of 0 marks a free page. And then we've got number of pages available, number of pages in the map, lowest address, highest address. So the way this memory manager starts up is it uses the information from Lamini to understand what pages have already been reserved by the BIOS and other devices, and turns those pages off. Which is why in the log we get this whole okay, yeah, we found 524,000 pages, but there's only 522,000 available because we discounted the reserved. And then, so get free pages, create the page bitmap, init the stats, kmem init, reserve pages, get address from page. And then that's our forward best fit allocation routine. Right, so the first thing we'll do then is off the back of the initialize, we're going to look for a place in memory where we can store all these page entries. I wonder if these need to be packed. And then I guess we'll have struct page entry enter. We'll call that an entry map. Contains a page entry page in memory. I guess if I wanted to, no, that'd be a waste. If I moved the status of the page into the struct, I couldn't represent that in 1 bit, so that would be a waste of memory. Get rid of all these standard C memory routines. So similar to this create page bitmap is where we'll have initialization of the page entry map. Kind of funny, I'm questioning why I used double underscore in here. It was the first module I did in C, and I may have been confused with something else. finds memory to store the memory map, allocates it. Store a pointer to it. So this will come after in its stats, create the page bitmap. This will go here. Get rid of that. So I'm not sure why they've got double underscore. Get free pages. All right. Oh, fly. My last stream on YouTube got demonetized because of the sound alerts, the way I set them up. So it recorded all of the music that was playing, and at the time I was playing a playlist that was all copyrighted music. Kind of sucky. When's your doctor's appointment, Fly? Is it this week? Okay, I'm just trying to refresh my memory over how I was allocating this bitmap. So I'm walking down the memory pages of the Lamini memory map, just checking if one of the entries can contain the bitmap, stuffing it in there, and then reducing the size. Entry max pages available. I guess we're just going to do the same. Twitch enable copyright music on VODs. Usually you can send two audio streams to Twitch, one music, one without, and use one for VODs. You can go ham and listen to what you want. Yeah, that's what we do. We have an audio split, so Spotify here doesn't send to the Twitch VOD channel. But we temporarily were listening to the all mix, which was the desktop mix. So it was sending the music into the VOD. What I might do, or what I want to do, is I want to dual stream to YouTube to save me exporting. The stream, when I turn it off, I have to wait 6 hours for the processing on YouTube, which then delays that stream being up for a day. So I have to go to bed. I can't do that until the following day. Why are you streaming? Why are you watching? Why are you watching? Ask, why are you streaming? Why am I streaming? So that people can see what it's like for someone who's never done operating system development before to start it completely fresh. Are you not entertained? But yeah, it's a fun hobby, and all the people in my domain, in the business domain, were like, "Oh, it seems crazy to get into OS dev. It's probably nuts to get into." Well, my friend, you are going to be Twitch banned. Thank you for outing yourself so fast. Enjoy the ban, buddy. Weirdo. All right, back to it. So allocating the entry map. So I think, yeah, we can just repeat this exact mechanism that we were doing. We'll scan the, I guess we'll do just another scan. I don't want to mix it into the create page bitmap. So that will adjust the entry length. So it'll be fine to double scan. Let's see. Okay, so let's do this here. We'll scan the map. We'll grab the entry. If it's an unusable entry, we'll skip it. Then we'll check the size, which we determined here. So this is what we'll need to do. We'll need to, how much memory do we need? Num pages in map divided by 8. Why did I divide that by 8? Convert page number bits to bytes. Oh. Right. Wait. Why would I divide the number of pages by 8? Oh, because um, why would I divide the pages by 8? Oh, because that's how many bytes we need. And a byte contains 8 bits, so we're just calculating how many bytes we need to contain all of the bits. Right. So for our page entry, so we're aligning this up to a page size. So we're making sure it's page aligned. We will take the size of the page entry struct. And we'll multiply this by the number of pages in the map. This is our map size. Which, at the moment, it's not that big. Kind of. Man, putting metadata in your memory manager is so... So let's just convert that to... So that's how many pages we're dealing with, and we've got 4 bytes. So let me just ask Google. So this metadata costs me 2 meg for a 2 gigabyte system. Which is fine. Maybe I should put that over here. So this metadata is approximately 2 meg for a 2 gig system, and then we can kind of readdress that. I'm going to put that on the struct actually, just so I'm mindful of that metadata cost. Better explain what this is. The page entry helps us determine how many pages our allocations reserve. We do a, is it a k-malloc or a k-alloc? It's a k-alloc. So the page entry helps us determine how many pages our allocations reserve when they do a k-alloc. This helps us know how many pages to free when we come to free that memory. As Bill Gates once said, 2 gig is enough for anyone. I was thinking today that, you know, what is it? It's 2024, and we're all thinking about if you were to build a new system, you'd probably stick, I don't know, if you're a developer, 64 gig of RAM. And if you go back 15 years, it was like 64 meg. So pretty sure that one day we're all going to be asking for 64 terabytes of RAM. Because, I don't know, it's probably going to be at a point in the future where your operating system is going to have its own LLM installed, and your GPU is going to be insane, and you'll be able to run a local AI assistant on every PC in the world. Where at the moment, that's all, you know, in the data centers of OpenAI. Okay, so let's carry on down here then. So we've got the map size. We've aligned that up to the page size of 4096. We should just dump this in the log. Say bytes. depends what dev I'm doing. For some stuff, 64 gig is minimum. I like to page stuff and only read from there. Yeah, it's an interesting point about working on low-powered, low-spec machines. Fly Mario, who's my mod, who's been a lifelong friend, we've been in this discussion many times about, for example, if you were programming games on old consoles like the NES or a Game Boy, um, it was actually fun for a developer having the constraints that you had in those small consoles, knowing that everything needed to be super efficient, compressed, and you didn't have this infinite amount of resources around you to be inefficient. Um, and now we just have so much resource, so much computing power, so much memory that we create disgusting stacks like Electron.js apps that run on Windows. It's like a lasagna of technology that just doesn't need to be there. But we don't care because we're like, well, I've got all this RAM, I've got all this computing power. It's like, a consumer level PC is browsing the web, maybe playing games. Um, Currently watching you using a 2-core, 4-thread NUC running FreeBSD. Wow, how are you? Um, I'm imagining that does not have CPU hardware level decoding. So I think what modern CPUs have in them now is amazing video decoding. The word I'm looking for, like there's SIMD in a processor to help it with concurrent operations. I think in like the latest CPUs, there's a bunch of operations that video decoders use. The same with encoding, though that's mostly on the GPU. Um, but yeah, going back to that point about abstraction levels, there's an interesting video on YouTube on the Primogen, and he had the conversation with a game developer who's been in the industry for about 30 years, and he's so talented. He just, whenever he makes a game, he doesn't use engines. He just writes the algorithms from scratch. Like his math skills are through the roof. Like he does shader programming, he does his own physics, his own engine framework stuff. Absolutely amazing guy. Um, but yeah, he talked about the primary reason why people get away with creating this stuff like Electron.js apps like Slack and Discord is there's nobody competing against them to put them to shame. You know, like if you were to write a C version of Slack or a C version of Discord, it would probably be insanely more responsive and stable. I mean, you would absolutely lose the portability, perhaps. But it I don't know. Like it's something I've been reading up on and I'm still forming my opinions about how much do you as a developer care about the CPU cycles your PC is doing since you have so many of them? Did you watch his handmade hero stuff? Yeah, he did that years ago. Like I remember that from 5 or 6 years ago. Where he did a YouTube series, I think, of showing you how to write a 3D engine from scratch. And that was inspiring to see that someone had that level of expertise and they would like demystifying why you just don't need to keep using engines all the time. Like you can just do it yourself. Yeah, I was an IRC frog like 20 years ago in the game dev channels on FNet. But uh, what is so Twitch chat is IRC based. I don't know. A lot of people don't know that, but I find it amazing that we're still on IRC every day because we're in Twitch chats. Yeah, we don't. There's no discussions in my job about the performance of languages or CPU cycles. I mean, I say that with a bit of a caveat. Like, it's got better since we moved off .NET and we've picked up Golang and now we write benchmarks. And because I'm now in a middleware, a back-end middleware team, we have some insanely scalable pieces of software, and you absolutely need to understand low-level memory allocation things. So, for example, our company uses distributed Erlang, and it has a cluster of those, and the amount of bandwidth and I/O, just general memory I/O, HTTP request responses per second, it's absolutely insane. It's not as big as Google, but it's a big enough system to challenge anybody. So some years ago, we were running Red Hat Linux, and even its memory manager was letting us down in that cluster. And we had to get knowledge of how the memory worked in Linux, and we had to turn features off. So it has something called like a I can't remember. It's like large allocation, where it does pages in the room of 2 meg allocations, and we ended up finding out that that was causing us a problem. We had to disable that in the Linux kernel, and we got a straight flat 20% uplift on the CPU processing for the cluster. So we have, it's cool to work in a company that has that um, concern. But I'm slightly off from that team where I'm in a payments domain, and it's not really about making massively scaled clusters of anything. There's a project recently I've picked up on though, and I've had to consider um, a lot of high throughput threading and memory allocation things for a queuing mechanism. So we've got some, we're introducing queues into some areas of the system, and those queues can be stacked into the millions. And then you have to think about the consumer who's then dequeuing at a rate that is as fast as the CPU can handle, and then firing database procs at a database as fast as it can handle. And then you have multiple of those, and then you're in a situation where you could be DDoSing your database. So it's fun now to be working in that space where I'm considering things like, trip switches and memory allocations per cycle, if you like, of the consumer, staggering requests and cooldown concepts of when you start hitting error situations and detecting error situations. Now we're using Kafka, so we have a lot of desire for real-time data events. So a lot of regulators in the betting industry require that you send events to their data stores before you can write anything away in your own data stores. So all the areas of the company need a real-time way of capturing specific customer events so that we can just send those Kafka messages to their data store, as well as send those messages down to our consuming services that put that data away into our data stores. So we've started over time introducing Kafka into a lot of areas of the business. And I think by the end of this year, we'll probably have all the main functions of the site or the product, if you like, all using Kafka messaging. And once we're in that position, we're going to have a ton of fun with some data lake stuff and some real-time escalations and real-time data notifications and stuff like that. Like hooking into the Kafka queues as, in real time. It's getting more observability, and visibility of your data flow in an organization. That concept in itself is a really fun topic, to chase observability. What are my systems doing? What's the throughput at that point in the chain? What's the back pressure from this thing slowing down over here? And when is this thing going to fall over because we've run out of RAM? But uh, our company are mad at ratifying um, every piece of technology that we use. So we don't just, look at something in the market and go, oh, that looks like an interesting product from Apache. Let's just drop that in. Like we have proper R&D that takes a long time to consider whether it's a true fit for what we need. I mean, hell, we've even, our architects have like banned certain features of Golang. Like we came off .NET, we came into Golang. We love how the language itself is simple, but they were straight away were like, we don't want you guys using mocking frameworks. We don't want you using generics. You can achieve everything you need to achieve without all of that stuff, and we'll show you how. So, we went on boot camps for simple Go design where we got better at unit testing, we got better at understanding benchmarking, and we got better at just letting go of the .NET and Java patterns that we had from, Ganga 4, that kind of stuff. We had to shed that thinking of Ganga 4 and come back down to very specific pieces of code that wasn't clever. And it works for a business domain. Like it absolutely works. I tell other people and they're like, that's crazy, like no mocking frameworks. And I'm like, yep, no mocking frameworks. Like we achieve our unit testing with function pointers. If you want to seam somewhere that you can't quite test, you just introduce a function pointer and redirect it at test time. I don't need to mock stuff anymore. So yeah, we've put a massive emphasis on simplicity now because we just hated the maintenance of humongous dependency injected systems and .NET patterns and oh no. So again, it's very dependent on the kind of company you're in. So for us to have downtime, for us to have a bug, it costs, 6 figures per minute of having downtime. Say like users couldn't log in or users couldn't place bets, then it's insanely costly. And the last thing you want is popping open some .NET code and having a developer that's not been trained or in that area of the system because we've just got so many systems now. There's a lot of places where we're blind in. You don't want to wrestle with design patterns and DI, um, an AOP based code, where it's all smoke and mirrors. Like anyone now can pop open Go code and just in its such simple writing form can just look at it and see exactly what it's doing. Like it just does what it needs to do. It's doing the do. There's no fancy pattern. There's no um, frameworks in the way. Just Go code doing its little simple thing of, oh, I'm just calling a HTTP service, right? And there's the data. It's like, oh, thank you. Anyway, let's get this map into memory. So if that length is greater than or equal to our map size, we're going to do all of this stuff. So that is going to be a pointer. It's going to be our entry map, which is the global. You know what I kind of miss coming into C? and I'm probably going to get hate for this. I kind of miss the Hungarian notation that I used to do in C++. I'd love to see, like G underscore here to just tell myself that's a global variable, or P for a pointer. But I could live without that one. But there's some elements of Hungarian notation that I keep feeling I need. Spent a lot of time in the e-commerce space on Black Friday, directed to turn the queues off, and that's why I had access, but because I didn't understand why there was so many messages in there, we lost a lot of money that day. Yeah, it's it's like areas of like that in businesses where systems going down cause you so much pain and money. Especially, I worked for Ticketmaster and it's the same for them. Like, imagine it's even worse. Ticketmaster will spend weeks marketing and advertising ticket sales for a big event like a Taylor Swift concert. And now they've hyped up millions of users to come to your website at 9 a.m. So now you've got the first problem you need to deal with is a burst of traffic from all over the world, right? So, problem number one, as a company, how do you handle that immense DDoS load happening on your website? Now, once you're past that and you've actually managed to keep your servers alive and they're not being set on fire by the amount of load that's coming into the system, now, how do you concurrently allow people to pay for seats in a stadium and book those seats in a contiguous fashion so that you're sitting with your buddies, one, two, three, four, party of four, and it's a highly concurrent system trying to book seats. Um, so there's like locking mechanisms that will slow the system down. So I don't know, having like performance scaling, having cool knowledge like that in those kind of businesses, I love those problems of performance problems. Um, and I remember working in Ticketmaster where we couldn't sell tickets to a World Cup rugby game, and the servers were just dying, and it took us 2 weeks to resolve handling the load of the users like killing the farm of servers. And I tell you, the amount of key things that we had to do, like using a cookie on the client's browsers to stop them coming to the server, doing client side blocking with a cookie. Um, like a complete poor man's queue. Like, you're in a queue. We don't know where you are in the queue. We don't know when we can let you in, but you're in a queue. But those environments are highly, well, it's a double-edged sword. It's highly stressful if you let it be stressful, but it's amazing fun and you learn a shit ton of knowledge. If you're using garbage collected languages like .NET 2.0 or 3.5, where introducing it was pumping link. So lots of companies were like, oh, look how cool and fun link to SQL is. And they're not realizing how A, disgusting the SQL statements were off the back of that, and B, the amount of garbage collection that was occurring in memory because of all the memory client side, um, you know, churning of objects. It was just all disgusting, and developers were completely blind to it. And then you get into a situation where you're using .NET to manage a thundering herd ticket sales platform, and now you've got all this problem of garbage collection killing you. So tech choices in those kind of companies and being very skilled at recognizing underlying architecture of all your technology um, requires, I think, quite a special kind of developer to have that experience. You're not educated in that experience. You're not boot camped having encouraged to have that experience, not even at uni level. It's something you'll only pick up in the field. Um, yeah. Uh, I've just realized actually my stream bitrate is showing to be poor. Is the stream running okay? I'm assuming it is since you can hear me. So we've got a spot, let's point here, we have to use it to kind of point it. Okay, I've kind of understood that now. We mem set the entry map size. That's fine. And then we reduce that by the map size that we calculated. We increment the base by that because we've taken up the space in that entry. And we're just reducing that stat there. Cool. So I think let's give that a whirl. That at least gets our entry map into RAM. Cool. So let's just check the log. Where's that size? PMM, page bitmap. Oops, I've made a mistake in that formatting. Is it LU, not UL? I keep forgetting. SAR. Yeah, it's LU. I don't use it that often, but I keep forgetting what the okay. Hello, Nick. Nice to see you. It's been a while. How you been? Okay, page bitmap size, page entry size. Yep, so that's our size of the page entry map. 2097,152 bytes. Just 2 meg. Oh, you're working right now? We're kind of having fun. We're not working. We're having fun. OS dev is fun. Okay, so we have allocated the page entry array for the number of pages. Well, that's not going to help us because we want to. It's actually bigger than that. I've made a mistake. Is it number of pages? Yeah, it is. That's fine, actually. You missed some streams. Good thing about the streams now is that they're all on YouTube. I'm not sure if you were here when I said that or you've seen me announce it, but all of the streams get auto uploaded to YouTube after I've done streaming. So you can Yeah, you can grab them on there if you ever need to. So they'll be there forever. Twitch was deleting them after 2 weeks, and it's not good. Okay, so we've done the map. Now, what we need to do is when we allocate memory, we need to maintain the map. So let me think about the state of this map. So we don't really care about keeping it valid because the specific page entry is going to get set when you do a calloc or a kalloc. The length will get set to a valid length here, and then when you come to free that memory, we can just look at what we just set in the page entry. So we know it's valid because we just set it. So we don't care about what else has been set. So I don't care about the state of this map on start at all, even though we've done a mem set and zeroed out the memory. Okay, so let me try and dissect what I was doing in here. Start from the cursor. Found a memory start. Let's try allocating from here. Allocated pages, pages state back to seeking, free page, it counts the pages. And if we have enough memory in here, advance the cursor for the next allocation. That handles wraparound, reserve it in the map, and return the location. So start allocation page is the index into the page, I believe. Allocation cursor, this cursor tracks the last page index where we allocated memory from. We allocate forward from this and loop back around if we go past the last page. Incoming off by 1 errors, I think. Reserve it in the map and return the location. Right, so reserve the pages. Start alloc page and number of pages. Now, this is going to be quite simple. So this is where we're going to, will that be? Yeah, it'll be a dot. Excuse me. Got a bad throat today. Let's go in mem. Nope. Let's go up here. I called it page len. I already don't like that name. I'm going to call it number of pages allocated starting at this entry. Now we can set that here. Allocated pages. Link from that. Let's track how many pages we allocated from here. Get address from page. Okay. I kind of don't like that being in. No, that's fine actually. That's fine outside the spin lock because that's just a location index, and that is not going to change. So we lock at the beginning. That's quite a juicy lock. Okay, now, so that has been done. We should be able to just implement the free now. So, excuse me. Uh, some thoughts here. If we pass in a memory location, how are we going to translate that back? So, get address from page. Lowest address into the higher offset. I'm wondering. So the first page is at the address of the higher half, I believe. But can I trust that? Because we record the lowest address, and that's a dynamic. Let's see where that's set. I think it's when I'm scanning. Yeah, we can't trust that because that comes from the base. There lies another problem. Hmm. How am I going to handle that translation? So all I have is a pointer to somewhere in RAM. And when I free, I would have passed that back in. And then it should know where the page index is for that. But I don't think I can translate it back because I'm missing context. Like I literally do not have the necessary information on that address alone to know where that is. Do we record? So I might record this actually. Lowest address, lowest memory location found from all memory map entries. do I write this? Get 3 pages, lowest address, get address from page. No, I just want to see if this actually comes out at 0. So when we do rkmem init, let's get this in here as let's do 0x hexadecimal, and we'll just dump that lowest address. So the problem here is we've not started learning about how to construct virtual memory. And we're being handed a memory map from Lamini, which is the bootloader. That's done a load of pre-work for us during the boot sequence. So I don't have any knowledge of how and what it's set up. Whether it's a contiguous thing starting at, as the first memory location starts at the higher half. I don't know. So let's just go see what that lowest address has dumped. Interesting. It's quite low. So that, if we just run it through, I should recognize what that means in hexadecimal by now. Put this in programmer. Let's just paste that here. Yeah, it's 4096. That's 4 kilobytes, as in 1 page. Highest address. Now, did we turn that off though? Guess I could dump the bitmap. Get 3 pages. Well, I need to do this after it's done all this stuff because this guy. Put some comments on here now we know what's going on. Next memory map entries, sending state with the bitmap with what it finds as usable memory. Okay. Find this page entry first in a bitmap. Start bit. Bitmap test. Let's just return a Boolean. Does. I just want to test if I've actually toggled off. The first page. I guess we can just remove that as a decimal. Okay. And we'll run that. Get a log. I really need to put some markers in this log file now so I can quickly navigate it. Result is 1. And I'm guessing that the bitmap itself took up the first clunk of memory in that first lower half. How can I verify this? How can I verify knowing that there's 500,000 pages? Actually, you know what I can do? I think I know what I can do. I can make an assumption with inversing the arithmetic in this function and see if I can get back to a page index from the memory address. Why these are all double underscored? What am I doing? So this will be get, let's see, that's from page. So it's get page from address. I'm just going to get ChatGPT to reverse the arithmetic in this. Can you reverse? The arithmetic. Um, we've negated what we added on with the VMM higher offset. We've negated the lower address that we also added, and we've divided by page size, reversing the multiplication of the page size. So this should get us back to yeah, it should get us back to the page. And then if this works, then we're fine. We can just carry on what we're doing. Now, the way to test that is I'll just make up I don't know, let's say page index is 100, and we'll go into the entry map at 100, and we'll set the pages allocated to 1, 2, 3, 4, and oh, but this relies on, oh, I need to do it. No. So with that code, let's just ask for how many bytes do we want? 20,000. 20,000 byte allocation gives us a memory address. And then we ask for the index, which is the get from that memory location. Now, we look in the entry map, that page index, and the pages allocated should be a sensible number. Now, let's put some stars on this so I can spot it in the log. Pages allocated. I think that'll do it. Where have we stored the bitmap? So yeah, we've stored it in physical memory. Did I predefine those functions somewhere? Hoping I did. Just grab this guy and move it underneath. Double score, right, so these are the name changes that I've done. That one there. There we go. LiliOS done? Yeah, sure, why not? It's finished. Okay, so check the log, and 5 pages allocated. So the way we verify that is the request that we put in for 20,000 bytes. Do that quick calc. 20,000 bytes in 4096 pages for exactly. Wait, let's put it in general. Does that really divide into that number perfectly? No way. No, right. So the align up will have put that to 5 and allocated 5 pages. The fact that that allocation, that memory address, just translated back to that page index and got us that perfect entry that we just set, it means now that we can perform a free. which is awesome. Holy crap, we can actually implement a free now, which is what we wanted out of this whole change. So I'm just thinking though. Yeah, it has to be that higher half offset is a complete contiguous array of memory locations for your RAM. It wouldn't make sense to have it with holes in and, you know, staggered, if you like. The whole purpose of that area of the virtual map is to be physical. If you think too much, your room will overheat and you will die. Thank you for that information, Fly. I am just going to fill up my water. I'll be back in just a moment. Yes, water. Oh, you're a Yorkshireman. What a beautiful area of the country to live in. Okay, we're cracking. We're absolutely smashing this. All expectations being met. This is awesome. So let's move this out of, whoops. So I guess it's just T. So using that, should I sense check this number? I guess you would do, right? If you're in something at super low level as memory manipulation, you're going to want to make sense of your numbers. Total pages. What's the stat that I've written at the top? Where's my total max pages available? I guess we will put that to the log. We'll put that in the log. I guess I should dump the address as well. Page index lookup resulted now from address. OX. Pass that P in. So that'll get dumped as well. And then we'll do hang and catch fire, which I think we've refactored into the kernel H. Okay. And then right now, number of pages, so we can just now loop starting from the page index. Now we can do bitmap off. Wait, we are setting the bitmap, right? Reserve pages. That's probably happening in here. Yeah. Okay. So I believe it wants pointed to the bitmap. Which is the page bitmap. And the location of the page is I. Yep, and then bitmap off I think does the calculation into the map. Yep, it does, starting at the param bitmap to 0. Okay. Put some comments in here, turn off all the bits for all the pages that were allocated. I guess. Oh, sorry. Yeah, you can't do less than 0. That's silly. It's an unsigned. I guess it's greater than or equal to. I'm not guessing. It's correct to say that it's greater than or equal to. If your max pages available is 1, the only index you have is 0. So if you become a value of 1 and you equals 1, you are out of space. Turn off all the bits for all the pages that were allocated. Shall we turn off? We could reset the entry map here. You know, we could set this to 0. I guess that would be good practice, just to give me peace of mind that I've actually, if I ever do some debugging in that in the future, that's now zeroed out. Okay, so that's our free. Freeze the pages allocated from previous. Okay, cool. What's the POSIX signature for free? Does anyone know? I need to keep my mind on keeping these signatures aligned to like the standard, what the standards, should I say? So what's the standard for? Let's have a look. Void PTR. So let's call it PTR. Oops. Yeah, okay, that's good. Looks good to me. Let's drop that in the memh. Oh, okay, you want it like that. Okay, well noted. Oh, I should call it K3, right? It's not a real C level free, is it? Amazing. Okay, so just replace that variable. So it is guaranteed in your implementation that an allocation block will live in contiguous consecutive pages. Yes, it absolutely is designed to do that, and it will fail if it could not contiguously allocate you. So there's a test here, for example, where it says, oh, I was counting pages for how many I need. And if it hits this pages taken, it goes back to a seeking state, and which resets the allocation to another point that it sees free in memory. And it's a wraparound cursor. So it's a cursor that just stays where it last allocated. You come in with a kmalloc and it just picks up from there, allocates, and then the next allocation again picks up from there and allocates again. But if for some reason you ask for so much and it couldn't do that, because there are some parts of the memory map that are taken up by drivers and things. So now the thing is, it is contiguous here, but I think when we get into the virtual memory manager, that's where things get a bit cool, and that's where things can be non-contiguous somehow. I don't know. I can't ever think of a reason how you would. No, it can't be. Like, it always needs to be contiguous. What am I thinking about? If you ask for 100 bytes, that 100-byte string, if it was representing a string, needs to be contiguous in memory. Like, it cannot not be. Um, so yeah, at the physical memory level, which is what we're doing here, this is all physical memory allocation. It's all contiguous. Now, in other operating systems that I've seen people develop, the interface into this kernel level allocation and free have been based on page numbers. And I don't know if that's going to cause us a problem, and it shouldn't do really. Like, we can just, we're asking for bytes, we can convert that to page numbers with knowing what the page size is, which we have here. But the interface won't stop us from doing stuff. It just, I don't know if that's standard or not. But saying that, a KLOC and a K3 isn't standard, so at the moment we're good, right? Now I need to test this free, though. We've written it, So how do we test it? I kind of need a debug. I need like a debug print that can print a window of the bitmap. And then I can dump like, plus and minus 4 bits around the allocated stuff that we did. And we'll print the window, see it turn on, and then we'll call the free method, print the state again, and then we'll see if it changes the window state. Which should be easy to do actually. Let's do that. Let's create an internal print bitmap, and we'll just say start and end. No, length. Do a for loop. This is kind of funky, but who cares? This is debugging. Bitmap test. Doing the page bitmap at the location I. If that's true, we're going to render 1. If it's false, we'll render 0. And then we'll dump the new line in at the end. Guess I'll do %d to %d. And we'll just shove in the start and start plus len. Okay. Let's state with bitmap. Specify indexes. Let's say indices, the plural. So we can now kind of, we're going to know where we first allocate though. Let's get some memory. So 20,000 bytes, 5 pages. How will we know? Oh, we can get the page index. It's quite high. Get page from address then. Now we can do print bitmap. We'll do I minus 2. How are we going to know how big that is though? Because it's in the page entry. Or should I say it's in the entry map and it's in pages allocated? and we'll do +2. Can do -4 and +4. Kind of like stretch the window out a bit. And then we free that memory. And then we print the bitmap. We'll also do a debug print of pages allocated. From the entry map. We may as well, because we have that information at hand. And then we free the memory, we print the bitmap again, and we'll look at the pages allocated again, and we'll see if that updated. Print bitmap is below everything. I know. Going here. It's not called free. Surprised no one caught that. Second call page allocated is 0. Correct, that should be 0. After that, key free. Is that... We've not done something important. It's very important. We need to lock during that free, because we can't have cores coming in messing around with the bitmap. Okay. So that's a locked piece of code. All right, let's run that and let's validate a log. Or do we throw page faults? You know? All right, everything ran. So there we go. We've got bitmap 12 to 21. Pages allocated fine. Bitmap 12 to 16. Wait, why did that change? Oh, because the original value changed. So we need to copy that. That's after the calloc. So let's just grab that value. And then pages +4 there. In the bitmap print, we'll do pages +4. Oh, you spotted that? Sorry, I'm in kind of like concentrated mode. I guess that's what you meant by second call page. Good spot though. Okay, let's grab the latest log. Let's have a look at that bitmap stuff. That isn't what we expect. If I... Okay. The indexes are correct. The pages allocated got updated correctly. It's just the bitmap printing, is that? Start is less than start plus length. Printing at that location. Why? I guess if we just do the bits that we've literally allocated, so I'm not confusing myself. So we've mallet, we're just dumping information. Bitmap test. I've not got an inverse, have I? Returns true if the bit specified location start of the bitmap is set to 1. Oh, you know what I'm doing? I think reserve pages. So a bitmap of 1 is allocated and a bitmap of 0 is free. That's fine. Okay, free, where are you? That clears the bitmap to 0. You know what? I could have unraveled a bug in my bitmap code. I don't think I've visualized it before. Wouldn't surprise me. Yeah, bitmaps 16 to 21 are all 0, even at point of allocation and then point of deallocation, they're all 0. That's not fun. I guess a way to we'll do a debug login here for now, and we'll just say bitmap on. For that bit number. I just want to verify that oh, I've got to be careful here. I think I know where I'm going wrong here. I'm just going to look at the log, and I think I've realized what I'm doing. Silly. I'm not mapping correctly between bits and bytes and page indexes. Whoops. That's going to murder the performance, printing every bit being turned on and off during the initialization of the memory manager. Yep, that's going to be there for a hell of a long time. 522,000 times 8. That is not a performing print function at all. So we can't do that in there. Let me just double check this print bitmap, and I've got a feeling. So that's the page number. The bitmap represents the page. So I'll get divided by 8. Oops. You should use memset for block setting. Yeah, we do. We that's during the initialization. Everything gets marked. That comment is not valid. There you go. So it sets every bitmap to 1. I guess what I could do here is just say print bitmap. I don't know, 10 to 20. Because at that point we've marked everything as on. This guy's gonna come higher. Let's bring you to the top, buddy. You can go there. What are you linking for? Oh, the Sinclair ZX81. I saw some tweets about that today. One being used as a door stopper, believe it or not. Or is it some kind of anniversary for the actual computer? Is that what it is? That's why I've been seeing it all over Twitter. Cool. All right. Bitmaps 10 to 30. There you go. So they're all ones. So the bitmap code isn't, well, that's the memset. You know what we should do? We should just play with that for a second, right? We printed the bitmap, and then if I do bitmap off at number what's the page bitmap in? If I do bit 15 and then print the page bitmap again, we should see it. And then we'll equally try and turn that bit off. If this works. So there you go. That worked. 10, 11, 12, 13, 14, bit 15 has been flipped to 0 in that dump. And then if we do bitmap on, and then we'll print the bitmap there. Yep, okay, that's working. Working as expected. So what isn't clicking? in our debugging. Right, let's try and stare at stuff. What I could do is in VS Code, man, I swear. Sometimes it irritates me. It doesn't navigate properly or give me proper IntelliSense. Okay, now when we allocate successfully, reserve it in the map, return the location, start alloc page. So reserve pages. We could go into here. Why isn't it control clicking for me? What has changed? So that's where we turn the bitmaps on. Can I do it here though? Will it kill on, will that murder the startup? No, it should be fine. Let's do this. Keep printf. Reserving page at start page. Plus another one. Pages. Okay. Should reserve pages iterate to pages plus start page? Oh, yeah, it should. How did you spot that, dude? Holy moly. I mean, I think what we were just debugging was going to land us there because we were just homing in on what was going to fail. But you've spotted it. Start page. Plus pages. Like, nice. Very well spotted. Let's just run that debugging code in the initialize now and just see if now that fixes everything. It makes sense that it might have been failing during the allocation because with an allocate only system, all I really cared about was getting back a valid memory pointer, and that obviously works, but I wasn't validating the state of the page map that I built. Oh, you looked at the Git? Dude, you are on the ball. Holy moly. Thank you. You know what, guys? At some point, I'm going to learn NeoVim. I want to have the experience of knowing what it's like to keep my hand off the mouse. I've never done it before, and I think it's about time we do it. Then we'll be a real engineer, be a real OS developer, a Vim-like IDE. Um, okay, so let's just double check what we're printing here. We're printing the bitmap here at I to pages, and then we're doing it again here. So we should see all ones, all zeros. Okay. Thank you for the follow. No accept. No exceptions. All right, let's check that log. Boom. Let's look for where we are dumping that memory. And there it is, ladies and gentlemen. Bug fix by a viewer. Holy shit. Amazing. So there you have it. If you're not already an operating system dev, no accept, you are now. You've just fixed the bug in one. Well done. Okay, so amazing. Not cool enough for Neo Vim, but I still use the mouse in Vim. Even after a couple of decades of using it, the mouse is just better at some things, like resizing splits or scrolling through code. Yeah, that's kind of my exact argument when I talk to people about who defend complete mouseless experiences. When because I've now started uploading my VODs to YouTube, YouTube is now recommending me other streamers, and I didn't know they existed, but there are other kernel developers on Linux that stream primarily on YouTube, and they've been doing that for like 10 years. So there's like these 3 hour VODs of kernel devs, and they're producing VODs like every day. Um, and every single one that I check or that I've seen, they're all just full screen Vim window. And when I see them navigating up and down lines and scrolling, it makes me cringe a little because I'm like, dude, I can hear you typing. And if I just had my finger on the mouse scroll, like I would beat you no problem. And then you get into that argument of, well, you've taken your hand off the keyboard, you know? It's like, so. I mean, it's an argument that doesn't even exist, right? People are not that elitist. They understand that it's just preference. So it's not even, it's just a bit of fun that I like to take poke at sometimes. Um, okay, so get all of that debugging stuff. That's a pretty good piece of work, actually. I'm really proud that we did this today. I um I love it when we complete like mini features like this because it's like, oh, I was productive today, you know? Like we've just implemented a good feature into the OS code, into the code base, right? And we did it. Um, yeah, I can show you one of the kernel devs. Code therapy. Here we go. There's this guy that it keeps recommending to me. And he's been streaming for like a decade. But he moves so fast, he's talking so fast, and he's navigating through his code base so quickly that I swear that's just an ASMR stream, dude. Like people are just turning that stream on, sticking him in the background, and they're like, now I can relax to his voice. Because he talks like crazy as he's deving. But what's interesting and what I'm thinking, it's like I don't want to be a YouTuber, right? I don't care for growing a massive community or anything. If people find me, you know, they find me. It is what it is. But all of his videos are using quite baity titles, like he's proper into the whole YouTube culture. Like, you won't believe what I compiled today. You won't believe what I did to my physical memory manager in today's stream. Oh my god. Shocking face. No, I'm not that way at all. I just literally published the stream and it just says OS Dev. We worked on the PMM tonight. Have fun. Um, I think little features like this, though, this is what I kind of love about sharing my code open source on GitHub and through streams and through YouTube, is that when I implemented the high performance timer, I was so humbled by somebody in the community said that they'd used my code to implement the same timer. And they shouted me out in the OS dev keyboard. They like shout out to Martin for his code. I've implemented the timer he's got in his code base because a lot of open source operating systems in the community haven't implemented the HPET timer. And I thought that was a good thing for us to do by ourselves to get into the habit of reading data sheets, specs, and getting into that mode of what does it take to use raw documentation to implement something. And because it wasn't like a crazy big module. But yeah, so some person used that and that was like, wow, holy crap. So implementing that free feature in today's stream, I think is going to be awesome for people to like, oh, how do I make my physical memory manager 3 pages, And as simple as just showing this really simple demonstration gives people that idea of somewhere to start. So what's fun for me in these iterations of memory management though is the virtual memory management side is so complex in other operating system code bases that I can't use any of it as a point of reference. It's so confusing to the lack of theory that I have that I stare at it and I'm like, what on earth is happening? Like in this code, like what are these domain terms? And I'm talking particularly about one operating system that I keep referencing, which is Lyra OS. Um, but yeah, that their memory manager is quite crazy. Like 4 modules that manage memory for them. They have a physical memory manager, they have the virtual memory manager, they have a slab allocator, and they have a memory map module. So there's 4 modules that interconnect to manage virtual memory. But yeah, so virtual memory, talking about the OS Dev wiki as well, like I was even trying to find pages in there to talk that was talking about virtual memory management, and it started to break down very quickly the quality of the document stuff in there, and it was all very high level theory based that I did find. There was no practical implementation stuff, and then there was stuff from 32-bit, old 32-bit code stuff. So a few days ago, I was like a little depressed about everything, and I'm like, oh God, where do I begin to even understand how to create a virtual memory manager? And then some guy was like, have you checked the software development manual from Intel? And I was like, oops, forgot about that guy. And the reason I don't like using it um, is because it's very hard to read. So I'll show you. Whoops. So the physical memory stuff in here. So it's another one of those topics where I ask people and they go, just read the manual, dude. And I'm like, come on, man. Like paging's huge. Like this chapter 4 on paging. Okay, it's just one chapter, but there's a lot of detail in that chapter. and you're not sure whether like, okay, it mentions 5 level paging. Shall I turn that on? Do I need it? You know, like and this is a problem with the SDM is that I don't know exactly what is important and what isn't important. It's a document that just says this stuff exists and it does this, right? It's like when I implemented the HPET timer. There's nothing in that specification that tells you that it's really bad to read from the main counter. Um, and you'd think that was a very obvious thing to do when you're developing the timer to use the main counter value, but it's really, really bad. Like it can halt a system bad. Um, so there's all these like learning experiences that people have in OS dev, and it's just in people's heads, man. And I think a good source is the Linux source code in places because um, they have so much good commenting around experiences of the hardware. They they talk about the founder bugs and the inefficiencies and the even the problems that are in QMU. So there's tons of good comments for the HPET in the Linux source code base. Yeah, being able to grok it is hard. Exactly, that's my problem. So there's like parts of OS dev, and this is something else I've learned from the beginning. If I was to encourage someone to start OS development, I'd absolutely recommend that they get some kind of mentor. Like have someone that they can freely have conversations with and have encouragement and have that person know the pains that they're going to go through. Like you know that for them to do a virtual memory manager, what kind of theory they need to know before doing that. And you can just save them so much time and pain. Um, what was I going to do? Yeah. Oh, so OS dev. I produced this diagram last night into helping me understand what the tree looks like of the page tables. So, and the reason I'm showing this is because we're going to start this next, by the way. So now that we're done with the free function in the kernel or in the physical memory manager, we need to start doing stuff with virtual paging tables. So a pointer that begins at the CR3 register in the CPU, and then we hit the PML4 table that points to many PDPT tables, which can point to a PD table, which then points to a page table, which then points to physical memory. And then the reason I was going to say, like a lot of development today is going to be a bit of a fuck around and find out kind of thing, because I don't know how much I need to allocate up front, right? So I think at least you probably need to do something like set the CR3, create a PML4, and then maybe what, one entry in the PML4, which points to one created PDP table and then creates one PD table and creates one PT table, which then points at one place in physical memory. You know, I could start there and then just see if it works. Um, or I could painstakingly go through this documentation and it might mention to me that you'll need to do this as a very minimum, you know, when using page tables. But I just think this is going to take a long time to truly absorb. 32-bit paging. Yeah, I've got a feeling from the documents that I've read about how it walks down the pages, or should I say the table entries. Um, as long as we have a connection between the tables, that every lookup point is succeeding, it shouldn't page fault. But what would uh, I wonder what the total size of the allocation is if you were to allocate a complete set of tables at their maximum capacity. I'm going to try and just quickly work that out just because I'm curious. Um, how large is the total memory for 4-level paging in 64-bit x86 coding if a table for every possible entry in every table type is allocated in physical memory? There you guys, what I'm looking at. The React-OS memory management code might help. It's Windows style. Oh, cool. And it's hilarious that it's actually telling itself that, okay, I got the facts, but I'm just going to go off and calculate this. There we have it. It's approximately 513 gigabytes. Um, so what that answers is you would not fully allocate a page structure. Um, now, because the page themselves, the metadata are all pointers, it doesn't matter where that table lives in RAM, as long as that it exists, right? So if your program needs to allocate more pages virtually, like in the page map, because the memory consumption is getting bigger, then you can just realize those pages, like you can allocate them somewhere else in physical memory. It doesn't have to be contiguous with the other pages, maybe. I'm guessing here. It's another assumption that we need to verify. But it doesn't need to be contiguous in RAM. Like as long as the pointers in the original high level, top level tables are pointing to the right locations in memory, then it should work out. Now, that also marries up with there's something else that was not mentioned maybe it was, I'm kind of lying. On the OS Dev Wiki, there is an instruction that we need to use, and I'm going to go find it in Lyra OS. So it's in the mem, it's in the VMM. And I think if I just search for ASM, this instruction here. So this INVLPG clears a table cache. So when the CPU is walking the page tables and it resolves an address, it caches that beginning and the end result and the target address in a table. So if at any point you screw around with modifying the page tables, you have to manually tell the CPU to say, hey, clear your table cache. And that invalidate page thing instruction, if we look for this, it says here, invalidates the table entries for a page containing M. And what's crazy about this instruction when you read it through here is that it may just flush what you asked it to. It might flush way more, or it might even flush the entire table. Like you can't guarantee that what it does. It's gonna flush, but it might just do way more than you asked it. So we have to bear in mind now. So we've got to introduce this when we're doing the VMM. It's funny because what I'm imagining about this whole situation is that it's probably a simple thing once you understand it. I can imagine experienced OS devs thinking, oh my God, it's just a 64-bit table. What is wrong with him? But it's really not. But that's the sense that I get from people when I'm talking about it. They're like, it's just a table, dude. I'm like, no, but there's so much happening. So, oh, that's a structure with 32-bit paging. Where's the one with 64-bit? PAE, is that it? CR3 to that, to this. 1, 2, 3. I don't think I've seen the 4-page table diagram. Okay, formats of CR3 and paging structured entries with 4-level paging and 5-level paging. So it's this guy. I'm going to take a screenshot of this and just drop it into my Discord. Just so I've got a place to put that. So yeah, I think the next step, there's just a bit more information that I need to gather from virtual memory, and that's the control flags on these entries here. There's a few bits at the beginning of the entry here, and I need to know what those mean. So let me just, there's a read write flag. Oh, there's a present flag at bit 0. Right, let's do some documenting because we're gonna absorb this quite explicitly. So bit 0 is our present flag, which is the entry is enabled or disabled. Bit 1 is user or supervisor mode. So that is access rights, I believe. Then there's PWT. I need to check what that is. There's PCD. And at bit 4. Wait, read write. No. Bit 2, 3. Excuse me, I've made a mistake. This is read write. Bit 2 is user supervisor. This is PWT, bit 4 is PCD. Oh, this is write through. And this is, what's CD stand for? I can't remember. Okay, bit 5 is A. Bit 6, IGN. Don't know what that is. Bit 7, reserved. Bits 8 to 10. IGN. Oh, ignored. Sorry. Or is it ignored? What's R4? On bit 11. IGN is ignored. Okay. It's just it confused me about the RSVD. Is that reserved or is that something else? I guess they just couldn't fit the text in, maybe. All right, now let's try and hunt for explanations. Protection keys, post-fault exceptions, access and dirty flags, memory typing. Translation look-aside buffers. That's the cache I was talking about. If anything, it's probably further up in the dock because it went through 32-bit mode. If that chapter on protection is about memory protection, I just want to see. Protection keys. Oh, they're here. Silly me. Read write is 0. Okay, writes may not be allowed to a 4K page referenced by this entry. User supervisor. Page level write through. What that stands for. Just update the notes there. Indirectly determines the memory type used to access the 4K byte page referenced by this entry. See section 4.92. Make a note of that, 4.92. Page level cache disable. Page level cache disable. Indirectly determines the memory type used to access by, okay, 9.2 again. Accessed indicates whether software has accessed the reference by this entry. Ooh. Dirty is that, wait, bit 6. Oh, this is the page table entry, so it could be a different layout to the other page tables. Indirectly determines section 4.1 and 2. Accessed and dirty are in section 4.8. Okay. Global. That's the bit that someone was telling me about. That where you can set page table entry as global. Oh, what did that drive? It's kind of like when you switch out virtual memory maps at the root level, which is the CR3 register, it won't, I don't think it flushes anything that has been marked as global, because what you're telling the processor is, even though I've switched my table pointers to a different table structure, there's a equivalent page entry because it's global, right? It's like static, or the word static in code. For ordinary paging, ignored. For HLAT paging, restart. If one linear address translation is restarted with ordinary paging, okay. For physical address entry, reserved, ignore protection keys. This may control the page's access rights. See section 4.6.2. Otherwise ignored and not used to control access rights. Okay. And then that bit 63 is execute disable. F1, instruction fetches are not allowed from the page controlled by this entry. Otherwise reserved must be 0. Okay. Now, what I'm kind of after is how do we get going? So this is like, okay, it's speccing out the structure, but how do we start putting the CPU in a state where it's got a valid page structure, and I can start walking the tables, you know? (32-bit paging, overview, enumeration of paging features, paging mode modifiers. Oh, that's cool. It's explaining the control registers, which I've never seen before. So CR4 and CR. Oh, CR0 is for supervisor mode and user mode. I realized I'm going backwards in the document, by the way. Could it be this? Paging mode enabling. Let's have a look. Bearing in mind that Lamini has already put us into paging mode on boot. So I guess a good thing to look at. You just try and run. That's weird. Where's where are the interrupts? Did I disable them somehow, or am I not getting them since I switched to UEFI? I wonder if that's a flag that I forgot to carry over. Run boot d ISO. Let's have a look. M Q35 M2G. CD-ROM boot D. Yep, serial file logs. Oh, I think it says -D. I bet it is. Without checking the docs, just hints at debug interrupts. Yep, we have interrupts now. Cool. That's a lot of interrupts just now. And that's our timer interrupt counting, which is cool. So the reason I've enabled that is because I want to check if we've got a CR3 pointer already set, which is this here. So the CR3 pointer is a pointer to the top level table. But interestingly, that's not a higher half physical address. So like these instruction pointers here are in kernel space. And I think that there is the higher half address. I say I think, I'm pretty sure it is. Like the GDT and the IDT look, they're in physical. They're in the higher half addresses. Hello, G Brown. Not Brown, sorry, just Brown. call you GB. How's it going, dude? So, I mean, I could check Lamini's documents for what it gives us on boot. I believe it might be in the protocol. For virtual. So at handoff, the kernel will be properly loaded and mapped with appropriate MMU permissions. As supervisor, the requested virtual memory address, provided it is at or above. Not sure what MMU permissions are, but it's the memory manager thing. It's going pretty good, actually. We've done some interesting stuff tonight. We've implemented um, a free function or kernel free for freeing memory, and we're trying to get into writing some virtual page tables. So it's our first experience into virtual memory. And we've got a little bit of theory. We understand how the page tables relate. We kind of know how those are represented in memory, like they're just 4K blocks. And I know that there's some control bits on each entry in the tables, but filling the tables is what's going to be interesting. Creating the tables, filling them with some data, setting them on the CR3 register, and then actually allocating some physical memory through the PMM, giving that to the VMM, and seeing if we can create a variable with a virtual memory address that writes to that physical. So I want evidence of the processor executing down the page tables of where we point it. So that's the thickness of theory that we're in right now. We're not too sure what the MMU is. We don't know what supervisor and user mode is, but we don't need to worry about that for now. Base revision 1, the above 4 gig HHDM mappings do not compromise memory map regions of type reserved or bad memory. So we're kind of like recognizing what these things mean now. So here where it says these all of its segments mapped using write-back caching at the page tables level. So that's a setting they've turned on for those entries. All higher half and the identity memory map regions are mapped using write-back caching at the page tables level, except for frame buffer regions, which are mapped using a write combining caching at page table level. The PAT page attribute table layout is as follows. So right behind, right through, no, right back, right through, not sure what UC is. I kind of don't understand those concepts yet. So I think we're going to have to zone in on that, actually, in the SDM. The MTRRs are left as the firmware set them up. Don't know what that is. Memory state at entry. RIP will be the entry point. Yep, that's cool. The GDT setup, the IDT. Paging is enabled, CL0, PE is enabled, PAE is enabled, WP is enabled, LME is enabled, and NX is enabled. Shrug. If 5-level paging is requested and available, then 5-level paging is available. LA 57-bit in CR4. Okay. A legacy pick if available in IO APIC IRQs. Any of those with delivery mode fixed or lowest priority or all masked. Booted by EFI or UEFI, boot services are exited. Okay. And then it goes down into the protocol request response stuff. Oh, that's an interesting paging mode feature allows the kernel to control which paging mode is enabled before control is passed to it. Okay, so I've not really gathered too much for that other than it's set a bunch of stuff on the control registers. And that it's loaded in some kind of virtualization, but it's only kind of pointed me towards the kernel mapping. No, not the kernel mapping, but the physical mapping in the higher half. Kind of confusing at the moment because of that value in CR3, which is, where are you? There. It doesn't look valid. I might ask the OS Dev Discord because the Lamani author is in there, I think. So they might know. But how I'm thinking about it is that it must be valid because the addresses of the pointers in C are pointing to the higher half in the virtual memory space. Right, so that there is a pointer in the virtual memory space, which the processor translates to physical RAM. What I was expecting from the CR3 register was that the pointer is to a table that lives in physical or a physical location. So I was expecting the that address to begin. But we might have to look on that CR3 register. It might be that I'm not understanding it correctly. CR3. Right, so yeah, it's the fact that it page directory base register base of the PDPT. How does it know where though? It's not to 11 of the physical base addresses are assumed to be 0. Bits 3 and 4 of CL3 are only used when accessing a PDE in 32-bit paging without PAE. So the first 12 bits, did it doesn't explain. Oh, we're at the 3-hour mark. So actually I need to call it there, which is okay. We got a lot done today. Did I push that work? Oh, I need to add that GNU makefile tweak. There we go. From that line, understand page tables can be stored anywhere in memory as long as there is available memory and it lines on a 4K boundary at canonical egress. Yeah, that's what we kind of thought about earlier. So I realized that the maximum size of an entire page directory is 500 and something gigabytes of memory. So you probably allocate as you need, which would mean that then your page tables could land anywhere in RAM. And as long as their pointers are pointing at valid locations to where the next table is located, and those entries are correct, and the CPU can walk down those entries correctly, then it makes sense, right? So RAM becomes fragmented, but the data's there. And it kind of makes sense of why I'm thinking what we can do as in a hello world memory setup is I've got to be careful not to trash the higher half address though. So like Lamani has already set up some paging and it's put the kernel in a certain location which is tracked in the pages somewhere somehow. I don't know. I need to figure this out. Um, I, I I need to somehow create my own page table entries without trashing the higher half setup. So there's a lot of theory and a lot of research that I need to do off stream, I think. So that next time I'm streaming tomorrow, we can just crack on and try and create a virtual page setup. And that does any reserve chunk of memory for page tables and being able to maintain a bit field to track variable regions is a reasonable approach to managing table storage. Yeah, I think what you're saying there is that you just probably have an initial allocation of entries then. Like you might say, okay, hello world paging setup is 5 meg, right? And it's like, I don't know, the first 32 pointers or the first 32 entries in the virtual space is allocated because you're going to use them for something. So you may as well just allocate them at the beginning. And I guess you can think about even when you start user mode and program loading, it's the same concept, right? You know, you don't want to give them here's one page entry. There's probably some minimum footprint you want to create for starting a process. Like here's your 5 meg virtual memory map. And it's probably up to you how big you want to create that. Interesting. Little things like this are starting to just like come into my mind and make sense. Like, oh yeah, it must work like that, right? So if I keep hammering at the where to start bit, I'll understand it in a few days, I think. Yeah, we've caught up on what the CR3 pointer is doing. We understand that that's the root pointer. So this diagram was from last night that I made. That's realizing the walk of the CPU. And we're aware of the TLB that needs flushing when you switch out the CR3 as well, and the global flag that keeps similar page entries in memory. But there's still ways to go. Like, I'm not confident on setting up this structure yet and filling it because I need to be aware of all the bits, if you like, in each entry. Like I think at some point in the virtual memory manager, I need to have control of turning certain bits on and off in each entry that I create, being aware of the bits and how to split the addresses up and put them in the right bit locations for the entry. But that resolution is probably something I'm not going to get until I actually start coding it. So I think at least tomorrow maybe we'll start just fleshing out an idea of what a PML4 looks like and see if we can get it pointing down this tree. I think even if I trash the higher half address, as long as the CPU isn't executing anything, let's hope anyway. If it's not accessing anything in the higher half, which obviously won't exist anymore, then we'll be fine. So as a small isolated test, we can create a really hello world structure, get the CR3 pointed, and then quickly do some memory read writes. And then we'll try and flip like the permission bits in those memory maps and see if we can cause a page full and see if we've got control, you know? Yeah, it'll get caught, I think, in the interrupt page full handler. But it'll be nice to see if we can successfully get a read write through the page setup and cause a full by turning the permissions off. Yeah, so that's been a really productive stream. I'm glad I streamed. I've been very reluctant. I don't know how you guys feel about this, but sometimes at the big, like for an evening, I'll think to myself, there isn't much I can code today. Like I'm just going to be popping open the SDM and I'm going to be sitting there reading for a couple of hours. But I don't know if that's worth documenting on stream. It's almost like a study stream, you know? It's like, okay, study with me reading about virtual memory. Is that worth doing? Would people find that valuable? Nobody else shows this stuff? Yeah, because what you're seeing here, Raw, is me full of doubt, right? I'm scared, right? I'm like, God, I'm going to look like such a noob doing this. But you're seeing it raw. You're like, what does a dev look like who's never done this before? Cracking open the manuals that I'm being directed towards. How am I digesting that information? And how does that, what does that struggle look like? Not enough OS dev content. Yeah, I guess. Yeah, it gives me some confidence then. I guess it is very valuable. That's why. Yeah, yeah, I guess I'll start streaming more then and doing some study-based streams. Um, cool. So yeah, tomorrow we'll resume here. We'll look into more on trying to create a Hello World page setup. So I'm gonna go get some food. It's kind of late here, but thanks for being here for the whole stream, guys, and seeing this K-free function being implemented, which was cool. You're often in the streams watching the code compile. Nice. Okay, I'll make note of that. G. There's a guy in the OS dev community called Ian. He is making a 64-bit operating system in pure assembly. It's called Bare Metal OS, and that's pretty inspiring and very hardcore. But anyway, so yeah, I'll definitely stream more then if you guys don't mind the study streams and me sitting here talking to myself trying to figure stuff out. And then we'll just see how it goes if people enjoy that on the tubes. But yeah, thanks very much for being here. I'll let you guys go now. Have a wonderful evening, and I'll see you tomorrow. Take it easy. Good night, guys.